Hi everyone, in today's lesson we're going to be looking at continuity, and the first thing we're looking at is the definition of continuity. And there's three criteria that you need to meet in order for a function to be continuous at a point. So we're saying that a function f is continuous at x equals c when, number one, f of c is defined. So in other words, when we say define, we mean that this would be filled in. We would also need to know that the limit as x approaches c of that function would exist. And so violating number 2, we have a picture demonstrating when the limit as x approaches c of the function does not exist. We have a jump discontinuity. And the third condition would be that when the limit as x approaches c of f of x, it's going to have to equal f of c. The two should equal. Right now, here's f of c. And here's the limit as x approaches c for that function, and they're different. They don't match. So if any one of these conditions is not met, the function is not continuous at x equals c. Now here's a really easy way to think of continuity. The graph of a continuous function can be drawn without ever lifting your pencil from the paper. So if you have to lift your pencil from the paper, the graph is not continuous. Now, in a previous lesson, we talked about types of discontinuity, and we're just going to add a little note about each of those. Some of them do have what we call removable discontinuity, and some are non-removable discontinuity. So for point discontinuity, and I have a demonstration of two graphs that have point discontinuity. So we're discontinuous at this point. We also have this situation where we're discontinuous at that point. But the thing you have to think about, it's removable discontinuity if you can add a point or move a point to make the function continuous. So if I'm chugging along this path and I can fill in that point and keep going and never lift my pencil from the paper, I have removable discontinuity. The same with this graph. I have removable discontinuity. Now, the next type of discontinuity is jump discontinuity. That's non-removable. You cannot add a point or move a point to make the function continuous. So I can't just put a point right here, for example, and now all of a sudden I don't have to lift my pencil from the paper. I do. So that jump discontinuity is non-removable. And the last kind is infinite discontinuity. That's also non-removable discontinuity. You cannot add a point or move a point to make the function continuous. We're going to go up this side of the graph. We have to lift our pencil from the paper. There's nothing we can fill in to continue drawing the graph. So in order to determine continuity, we will be graphing some rational functions, and you need to have some recollection of things that you may or may not remember from the past. So the first type of thing we're going to look at are holes and how you end up with a hole in the graph. That means that we have a discontinuous part of the graph where the line sort of skips over a part. And if we're looking at equation to determine if we have a hole, here's our first example. So in other words, I could cancel out x minus 3 and x minus 3, and I would end up with y equals 1 over x plus 5, but we have to remember that we have a hole at x equals 3. I mean, you can't just turn this into this without recognizing that we still have a hole at x equals 3. Now, for the next example, we would be able to cross off x minus 2. And we would also be able to cross off one of the x's. So we'd have a 1 up here, and we'd have an x here. So our new equation would be y equals 1 over x. So we'd have a hole at x equals 2. And we would not have a hole at x equals 0 because we still have the x remaining in the denominator. The next thing you need to remember is vertical asymptotes. A vertical asymptote is a discontinuous part of the graph where the line cannot cross over, and we represent that by usually a dashed or dotted line. So if you look at this first example, and a vertical asymptote will occur at the zeros of the denominator. So if I set x minus 2 equal to 0, and I solve for x, I know that I have a vertical asymptote at x equals 2. Now looking at the second one, you can see that I'm able to cancel the x's. That means that I'm going to end up with y equals 1 over x minus 2 times x plus 5. So I can't forget that I did have an x originally in the denominator, so I have a whole at x equals 0, and I have vertical asymptotes at the 0 of the new denominator, so I would say x minus 2 equals 0 and x plus 5 equals 0. So I have a vertical asymptote at x equals 2 and at x equals negative 5. So if you can cancel out a term, then that is going to become a whole. Otherwise, if it stays in the denominator, it becomes a vertical asymptote. So if we were to go back and look at this guy right here, we had 1 over x, we had a vertical asymptote there at x equals 0, not a whole. And the last one is just a reminder of horizontal asymptotes. And we're going to be comparing the degree of the numerator to the degree of the denominator. If the degree of the numerator is greater than the degree of the denominator, here we have x to the second and x to the first, there's no horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, so we have a 1 and we have a 3, 1 is less than 3, we have a horizontal asymptote at y equals 0. And if the degree of the numerator is equal to the degree of the denominator, if we were to multiply out the denominator here, we have 5x squared. Don't worry about the rest for now. The first term in the denominator would be 5x squared, and we'd be, again, comparing the degree of the numerator to the degree of the denominator. If they're the same, we're going to be looking at the coefficients. So the horizontal asymptote here would be y equals 4 over 5. So the best way to learn is to look at some examples. For the following rational functions, and that just means we have a ratio, we have a fraction, find the vertical asymptote, the horizontal asymptote, and the wholes for the graph, if any. So first, what we're going to do is factor the denominator. So we've got, and we want to see, is there anything that we can cancel? Well, there's nothing that's the same in the numerator and the denominator. So I know for sure that I don't have any wholes. The next thing I want to look at is vertical asymptote. Well, the vertical asymptotes occur at the 0 of the denominator. So x plus 1 and x plus 5, if I set them both equal to 0, I'm going to get x equals negative 1, and I'm going to get x equals negative 5. Now, it's really important that you write x equals. Vertical asymptotes are lines. They're equations of lines. If you just write negative 1 and negative 5, it can mean anything. It can mean a point. It could mean it's a horizontal asymptote. So you have to be really careful that you include this x equals part when you're writing out a vertical asymptote. And the last part is the horizontal asymptote. And the horizontal asymptote, we're going to compare the degree of the numerator to the degree of the denominator. So we're going to compare the degree of the numerator to the degree of the denominator. I have a 1 here, I have a 2 in the denominator, so the degree of the numerator is less than the degree of the denominator. So that would be this case here. And that means that I have a horizontal asymptote at y equals 0. All right, I would say try letter B and come back when you're ready. First thing we're going to do is factor the numerator. And then we're going to see, do we have any wholes? Okay, well, I can cancel x minus 2, and I can then rewrite the function, keeping in mind that I am going to have a whole at x equals 2. So when I draw the graph, I have to remember to put an open circle where x is equal to 2 on that graph. Now we're going to look at the horizontal asymptote. Again, we're comparing the degree of the numerator to the degree of the denominator. 2 is greater than 1. So we have this situation. So we have no horizontal asymptote. And you can also just consider that the revised function, this guy here, is just the equation of a line. There's no horizontal asymptote when we're looking at the equation of the line. We will have a hole at x equals 2, but the rest of it's just a line. And then the last part, we're looking at a vertical asymptote. When we do that, we're not looking at the original function. We have to look at the revised function. And we don't have a denominator in our revised function. We've taken care of this x minus 2 by noting we have a hole there. So for letter B, we have no vertical asymptote. And again, if you just think of the equation of a line, there's no vertical asymptote with an equation of a line. Right. For number 2, it says examine the graph of the function below and determine if the function is continuous. If it's not continuous at any point, classify the discontinuity as point, which is removable discontinuity, jump, which is non-removable discontinuity, or infinite, which is also non-removable discontinuity. All right, so the first thing we want to do is graph this. And I think it would be helpful to do the process we just did with number 1. Let's first factor it. And we can see that we have a term that's going to cancel. So we know that we're going to have a revised function now, but we're going to have a hole at x equals 1. And the new revised function is just the equation of the line, so we're not going to have a horizontal asymptote, and we're not going to have a vertical asymptote. And then we just want to pick some points, and so we can just pick points and put them into the revised function right here. And we just want to be very careful that we include the value of x equals 1 in our table, and we want to note that where that point would fall, but that there's going to be an open circle there. So let's say we'll just pick a couple of random points. -4, if I put -4 in there, -4 plus 1 is -3. Maybe I'll put 0 in there. I get 1. If I put 1 in there, right? If I put 1 into my revised function, 1 plus 1 is 2, okay, but I have to remember at x equals 1, I have a hole. So on my graph, I have to draw an open circle. And let's just put one more point in there for fun. I'm going to pick 4. 4 plus 1 is 5. Okay, so let's plot all of those points. And you can see that at the value of x equals 1, I've drawn an open circle. All right, we have our graph all drawn here. Okay, the next thing we want to look at is this graph discontinuous? Okay, well, we can see that we have point discontinuity occurring right here, right? That's point discontinuity, and that's happening at x equals 1. And we know that point discontinuity is removable. If you can add a point or move a point, it has removable discontinuity. So for this guy, point discontinuity at x equals 1, removable. All right, now this last page is really important. Try to stay awake here and really listen to this last page. This is a very important concept to get. The notion of continuity and differentiability is a pivotal concept in calculus. Recall that when we looked at graphs of when a derivative does not exist, we examined discontinuity. When a discontinuity exists at a point, you cannot have a derivative at that point because with differentiability, you must be able to find the slope of the function at that point. So here we go. Listen in now. When a function is differentiable at a point, then it is continuous. But a function can be continuous at a point and not differentiable at that point. So right now, you're probably thinking, I'm crazy, and you have no idea what I'm talking about. But don't worry, we're going to go through these 4 examples, and it's going to really help. So let's examine the idea in the practice below. For each graph at the given value of x, is the function differentiable? continuous but not differentiable, or neither continuous nor differentiable. All right, so we're looking at this graph, and it's just a line. There's no breaks in the graph. We never have to lift our pencil. We have no discontinuity. All right, so we know the graph for sure is continuous. Is there any place on this graph where I couldn't draw the slope? Okay, well, I could draw the slope anywhere on this graph. So that means that function is differentiable everywhere. Write that down. And so everywhere on this graph, we were differentiable and continuous, but they were specifically asking for at x equals 0, and it certainly is differentiable and continuous there. All right, let's look at the next graph. All right, so now again, we're looking at x equals 0. We have a vertical asymptote at x equals 0, so we know this graph is not continuous. And we also want to know, is it differentiable? Well, we know that a graph cannot be differentiable when we have what's called that infinite discontinuity. So let's just make a note right here that we have infinite discontinuity. So this graph is neither continuous nor differentiable at x equals 0. Now the next graph, we're being asked to examine the graph right here at x equals -1. Well, if we look at this graph, we're certainly continuous on this graph. We're never going to have to lift our pencil from the paper. But if you remember, a function is not differentiable at a corner. All right, so let's make a note about that. So the derivative does not exist at a corner, so this function is continuous but not differentiable at x equals -1. And the last one, we're looking at x equals 1. So we're looking right here. So we have a point where we have a discontinuity. It's removable because we have point discontinuity. But it is a discontinuous graph. And we're looking to see now next, would we be able to draw a derivative at x equals 1? Well, we said we can't draw a derivative when there's nothing there. There's nothing at this point on the graph. There's a point down here, but that doesn't help us. This point would need to be filled in. So we have point discontinuity, and at x equals 1, this function is neither continuous nor differentiable. Now, I would say that the concepts that we went over in this lesson are sometimes particularly difficult to grasp. And even if you feel pretty good about it right now, a couple days from now, you may forget again, and you really want to make sure that you have these notes handy as a resource for you whenever we go back to talking about continuity, removable, discontinuity, or comparing continuity versus differentiability. All right, everybody. Thanks for watching. Have a great day.